Hi guys, welcome to our channel of Sciences and Mathematics. Today we're going to look at a concept in aromatic chemistry, and it's going to deal with, of course, the reaction of benzene and its derivatives. And this specifically is going to pertain to electrophilic, of course, substitution, which occurs on the structure of aromatic compounds. But in this case, we're going to use benzene as one of the organic compounds or the aromatic compounds that we're going to use in this particular discussion. In that case, of course, we know that there are different kinds of reactions that occur in as far as organic compounds are concerned. But in this case, this is going to give us a basis for determining on how other reactions that entails organic compounds, specifically aromatic compounds, happens. So without further ado, thank you and welcome. So as I've mentioned, today we are going to look at a topic in aromatic chemistry that deals with the electrophilic substitution of aromatic compounds. But of course, as we have said, we are going to use benzene as our representative compounds. Of course, we know there are other similar ring systems that are referred to as aromatic that we're going to learn in one of the topics that we're going, or the concept we're going to talk about, aromaticity. So as I've said, we're going to learn about this is a topic in aromatic chemistry. And as we have said in one of our videos, is that aromatic compounds are compounds that are similar to benzene, or just like benzene and the similar ring systems. So in this case, we're going to see also that there's an additional or something or an additional information we're going to add to that, and we're going to define it in one of the few recaps that we're going to have before we start our discussion. So in that case, I will just go ahead and start with just a few recap that is going to assist us understand this concept of electrophilic substitution of aromatic reactions. So the first one that I'm going to mention here, I've said about the term, so I can just like this is electrophilic substitution reactions. So in that case, this is the concept that we are going to learn concerning these aromatic compounds. So I've mentioned about a few terms that we're going to look at. The first one is an electrophile. And this basically refers to an electron-poor species that of course will react with the electron-rich species that we are going later to mention about the term nucleophile. So as we can remember, this suffix comes from the term loving, so like electrophile, diophilus. So this is a term that is used to refer to something that has a tendency or liking for. So this one is an electron-poor species, so in the actual sense it attracts, so yeah, or it has a tendency of attracting electrons, while this one is an electron-rich species. So in that case, there's another term that we are supposed to know before we just have a discussion into this, and this term is concerned with the term cation, carbocation. Now, as we can look from that specific term, we can see that that one pertains to the term charge, which of course refers to the positive and negative charge. And in this case, when we talk about a carbocation, this refers to, of course, a carbon atom. This refers to a carbon atom that of course has a positive charge and 3 bonds. Of course, we have mentioned in one of our videos about the concept of stability, and of course that is the octet rule, and we say that carbon as an atom, especially for the first member of the aromatic compounds that consist of a single atom, has got 4 bonds that are covalently bounded to the carbon. So in that case, if we try to look at this, we see that there is a hydrogen that is bonded to this. So in case maybe we have 3 hydrogen atoms at that point, then we will have a partial charge for the, or just a positive charge at this center here, that is a carbon. So this kind of a molecule is what we refer to as a cation, which is a carbon atom that has got a positive charge and then 3 bonds. And then we are going to talk about the concept of resonance stabilization. Resonance stabilization. Resonance stabilization actually is a concept that whereby the stability of species that gains, or as we can mention, is the stability that a species can refer to, maybe just like a carbocation or something like that. A species gains from having maybe a charge delocalization through resonance contributors. Of course, we're going to look at the concept of resonance contributors, but what we should understand for now is that the concept of resonance means that this is a kind of stability, which of course a species, maybe that one can be just like a carbocation we've mentioned, gains from having charge delocalization. So in this case, of course, we are going to look at another concept that is used in this case or in the electrophilic substitution reaction, that is known as an intermediate species. An intermediate species. I think I'll use this so that I make a difference. So for an intermediate species in a reaction is a molecular entity that is arising within a sequence of steps in a chemical reaction. So which means, for instance, if I have a product A that is forming product C, but there is an intermediate species that is formed in between, which is of course a molecular entity, then we refer that one as an intermediate species. So in that case, we are going to encounter a range of intermediate species in our reactions, and then we are going to maybe have a look or a reminder of what we have discussed attaining that. But for now, let's just have a concept that the term intermediate species refers to an entity or a molecular entity that is arising within a sequence of steps in a chemical reaction, of course, which we are going to give another term. So there's also another one that we are going to look at, another concept, that is the Haeckel rule. Now the Haeckel rule, this one is named, of course, after there's a physicist who used to work so much with the concept of course, molecular structures, and of course he proposed a rule to help to determine that the planar ring molecule will have aromatic properties. So this rule states that if a cyclic planar now means this is derived from the term plane in geometry, which means that it's a two-dimensional structure that runs in 4 directions indefinitely. So if a cyclic, planar ring molecule, so there are 3 terms here. If a cyclic planar ring molecule will have aromatic properties, so it will have the number of electrons demonstrated as 4n plus 2 pi. So in this case, this will be the number of electrons in that ring, of course, a planar cyclic ring. So in this case, if the number of electrons form this or obey this kind of a formula, then we say that it obeys the Haeckel rule, and that kind of a molecule will be referred to as aromatic compound. So in this case, of course, as I've mentioned, we are also going to mention some of the terms. Now I can use this simple and this one. This one refers to as sigma. sigma, and this is pi. The pi, the constant that we normally use in mathematics, that appears in mathematics and physics. So the first term or the symbol that I've used there is the sigma and pi. So these two terms will be used insofar as the covalent bonding in organic compounds is concerned. So in this case, when we talk about a sigma bond, this is a bond that is formed by linear or coaxial. So this one forms due to the overlapping of atomic, that is the overlapping of atomic orbitals. And geometrically, we have said that the overlapping of these atomic orbitals is a coaxial. A coaxial in nature, or the one that is linear. Linear, of course, means which are in a straight line. So in this case, when we're talking about the sigma bond, it refers to the covalent kind of bonding that occurs when the atomic orbitals interact by overlapping at the linear geometry or the coaxial. So when we talk about the pi bonds, these will be bonds that are formed by parallel or lateral, lateral. Lateral means side by side. So in that case, when we talk about the pi bonds, we mean that these are the bonds that are formed by parallel or lateral overlapping of atomic orbitals. So in that case, I'm just going to give a small demonstration for the concept I've talked about. That is about overlapping of the orbitals, atomic orbitals. By now, I hope that we have learned about the concept of orbitals, which are, of course, probability in space where there's a likelihood of finding electrons. So if I give a demonstration about the carbon, just give a carbon-carbon bond, I can be able to demonstrate or to just show the orbitals around these carbon bonds, just in a simpler way like that. These are the p orbitals. Of course, we know that the s ones are circular or just spherical in shape. So in this case, if we have p orbitals along those planes, we talked about four bonds. So there'll be an interaction between this and this orbital that is, of course, facing each other, and then the electrons of these orbitals will interact in this sense, and then we shall have other overlapping of this nature, of course. So in this case, this is the first one that we were referring to as the coaxial or linear overlap of orbitals, and we say that this one, of course, is known as the sigma kind of bonding. And then for the second one that we have drawn for these two parts, this is a pi bond and pi bond. So whenever I mention the term pi plus sigma bond, it will basically be referring to those two concepts. So in this case, and then this one, of course, I've said it's a lateral. This is a lateral side by side. And then for this one, the sigma bond is a linear overlap of atomic orbitals. So in this case, there's also a term that I'm going to use in this discussion, that is the term arene. The term arene. So whenever I mention about this, basically refers to benzene and its derivatives. So this one can be a single substituted, double substituted, or polysubstituted benzenes. So in this case, whenever I mention the term arenes, that one refers to those kind of term. And then I've talked about the term collinear, and then I've talked about the term parallel. So in this case, we're going to see that the structure of benzene as one of the representative of aromatic compound that we're going to use in our discussion has got what we call a planar structure. And I said about the concept of the term planar comes from the term plane, which is a two-dimensional figure, or just a dimensional figure that runs in four directions indefinitely. So if I've reduced it to this kind of a boundary, this is just, I can call this one is my plane, maybe a plane A. So this is the area that I'm referring to as a plane. So for a molecule that has got the structure of a planar, and which means all its atoms lies in a plane as I have demonstrated above. So therefore, a planar molecule is when all atoms of that molecule lie in the same plane, and that is, as I've mentioned, the term plane from the normal geometry. It's of course a two-dimensional structure that runs in four directions indefinitely. So in that case, of course, as we have said about the electrophilic substitution reactions, so therefore I've defined the term electrophile, and lastly I'm going to look at the term substitution. So as we said that organic compounds can be either the chain, they can form chains, can form cyclic compounds, and then we said they can form cyclic compounds, chain compounds, and specifically this is what we discussed when we were talking about the nomenclature of organic compounds. So for this case, we are going to look at the second concept, but we said that these compounds like benzene, which of course I'm going to draw here, has an alternative double, single and double bonds, and this is a line structure. Of course we talked about for the chain compounds. If we are trying to represent a compound with 4 carbon atoms, we can use a line structure, either compressed formula, line drawing, or maybe the expanded formula. In this case, this benzene has been demonstrated using the line structures, which is a cyclic compound with alternating single and double bond. So this structure of benzene, of course, is going to lie under the cyclic compounds. And now for the term substitution, we know that the molecular formula for benzene, as I've drawn it on the board, so this is a structure. I'm going to write the molecular formula that I've mentioned. So benzene is written, the molecular formula for benzene is C6H6, which means for these alternating points, for the single and double bonds, there is a single hydrogen at this particular point. Now, whenever there is a different molecule that has reacted with this, or it has undergone a reaction or a substitution at that particular point, or basically meaning replacement by another molecule, then that was what we call a substitution reaction. So therefore, whenever this hydrogen, this ring of hydrogens are substituted maybe with another compound or maybe a molecule, then we refer to that one as a substitution reaction. So that one said and done, we can now basically just look at a summary of the concept that we were discussing about, that is electrophilic substitution reaction. Now in this case, I presume that we understand the term electrophile, what the concept of substitution means, and what's an aromatic compound. So in this case, for electrophilic substitution aromatic reactions, as I've said, we're going to use the symbol for electrophile, which is an electron poor species, which is of course will now be a positive charge, since we say that electrons are negatively charged. So the deficiency of electrons means this compound is positively charged. So we shall use this symbol for electrophile, and we shall have this benzene structure at this particular point, having in mind that we're going to have a substitution reaction. So whenever I'm not showing the hydrogens at those specific points, we just have in mind that we're having hydrogens at those specific points. So whenever that electrophile interacts with that benzene molecule, of course we said that in our aromatic nomenclature, we said that the functional groups dictate the chemical and physical properties of a compound. So in this case, if we are having benzene that is reacting with an electrophile, then we will have benzene that is reacting with an electrophile to form a compound or a product that has got that E, which is an electrophile attached at that point. So we talked about the automate and the para positions of the benzene, and that one we looked at in one of our videos. I'll just put it in the link in the description box of this video so that we can have a recap in case we need to do so. So there are 3 steps involved in this electrophilic substitution, of course, and we are going to look at these particular steps. So in this case, this general reaction represents an electrophilic aromatic substitution, but we are going to see that basically this molecule of benzene can be represented in two different ways. Now the first one is known as the Kekule structure. This is from the, of course, the German physicist, who was also a chemist, of course, who came up with the chemical structure for this particular molecule, and then it was known as Kekule structure. So we are going to discuss this one later, but this is a representation of the Kekule structure, and this is a Robinson structure for benzene molecule. So in case we use these ones alternatively, they are just but the same kind of molecules that we are referring to. So in this case, as I've said, there are three basic steps that are going to be involved in this kind of electrophilic substitution reactions, whereby hydrogen, one of the hydrogens has been substituted by an electrophile. So in this case, we are not going to indicate this hydrogen is there. So in this case, it's absent and it's been substituted by an electrophile. So the three steps which are essential for this kind of a reaction to take place is that the first step is that there is a formation of a new sigma bond from the carbon-carbon bond in the arene nucleophile. So now that I've defined the term sigma bond, and then I've defined the term nucleophile, and then the term arene. So in this case, the first step dictates that there's a formation of a sigma bond in the carbon-carbon double bond in the arene. Arene, I said, is benzene, can be substituted benzene and its other similar compounds. So there's a formation of a sigma bond in the carbon-carbon, of course, this part of the arene molecule, which we are referring to as arene nucleophile. So this is an electron-rich species that is interacting with an electron-poor species. So in this case, we can be able to use, of course, we're going to talk about the reaction mechanisms, and we're going to see that a reaction mechanism is a stepwise procedure that happens from the reactants to the product. So in this case, this first step implies that this part of the arene molecule interacts with that one in order to form what we call a sigma bond that we have already talked about. Then step number 2 is that there's going to be a removal of a proton by breaking the sigma carbon hydrogen bond. Of course, we talked about the carbon hydrogen bond at this particular point. So step 2 implies that there's going to be a removal of the proton. Proton, in this case, we are referring to the positively charged. So this is the hydrogen which is being referred to the proton part of this molecule. So the removal of a proton by breaking the carbon hydrogen, which is a carbon hydrogen sigma bond at that particular point. And then the last step is that there's going to be a reformation. So this one, of course, implies that there's a formation of a sigma carbon. There's going to be of course, the removal of the proton, this proton that is attached to the hydrogen, which is of course a sigma bond from that point. And then step number three is that there will be a reformation of the carbon hydrogen. There will be a reformation. There will be a reformation of this is a carbon of the arene double bond, and the restoration of aromaticity. I hope this one is feasible from there, but this is restoration of aromaticity. Now this one implies that for this molecule to be stable, it has to regain we're going to talk about the stability of aromatic compounds and why aromatic compounds, of course, are stable as compared to others. So in this case, of course, this one was trying to depict the concept of a reaction mechanism that is representing this whole reaction of an electrophilic substitution aromatic reactions. So in this case, we're going to do a reaction mechanism that is going to represent this step. So as we have said in summary, so the first step is the formation of a sigma bond in the carbon-carbon bond, which is a real part of the arene nucleophile. And then step number 2, there's going to be a breakage of the carbon-hydrogen sigma bond at this particular point by the substitution of that's a proton that we have talked about. And then there's a formation of the carbon-carbon double bond and the restoration of aromaticity. So in that case, for these steps, I'm going to do away with them. And then we discuss about this reaction mechanism that I've talked about for that kind of a reaction. So I'll just do a quick demonstration. Still, I'm going to use that that representation that I've given that is above. So we have that one. I talked about the concept of an intermediate species. So there's going to be an intermediate species that is going to be formed at that particular point before we have a final product, which is going to be an electrophilic substituted aromatic compound. So we have this is positively charged. And then we said we're going to talk about the concept of resonance, whereby these bonds, because this molecule can be represented either by putting these bonds here or just the same. This one is just the same as that one. So then we have this intermediate product that is formed at this particular point, whereby there's an electrophilic substitution at that particular point, and then we have a hydrogen. So when you talked about the concept of stability for the carbon atom, the 4 bonds there, so in this case there's this 1, 2, 3, 4. So there's a proton, and then there's an electrophilic substitution at that particular point. So in this case we are going to have a negatively charged species, which we can represent as being negative for a nucleophile, that is going to pick a proton, this proton from this particular point, and then these electrons are going. Now for the first step that we are, maybe I'm tending to which are presumed to be just put from that. So this is the arene part of the carbon-carbon double bond that is picking the electrophile or attacking the electrophile from that particular point. And then we have a substitution at this point with the hydrogen. So this nucleophile just picks the proton from that point, and then this bond goes back to restore aromaticity. And then we can remember that from this carbon bond, whereby the breakage or the electrons had been removed, there was a positive, partial positive charge at that point. And then the last product, we shall have, of course, this electrophilic substituted compound, which is written as that one. So that basically is a reaction mechanism that is representing this nature of a reaction that we're referring to, electrophilic substitution. And of course we can say that for that case, the first step that we talked about is the formation of a reactive electrophile, which of course I've just demonstrated there. And then number 2, there's a slow reaction of the arene carbon-carbon double bond with electrophile to give a resonance stabilized structure. This is a resonance stabilized structure. We talked about the concept of resonance, whereby we're going to demonstrate maybe this kind of a charge can be at this point, or another point, and then we shall have those double bonds assuming different positions. Now in this case, of course, this the determining step that we're going to look at, and then the last step we talked about at that particular point is the loss of hydrogen or the proton from the carbocation to restore the carbon-carbon double bond and the aromatic system. So I've talked about the concept of resonance stabilized molecule. So that is maybe going to be the last bit that I'm going to demonstrate using some kind of or this reaction mechanism, so that we can be able to understand it. I hope this mechanism, the concept for electrophilic substitution reactions, we have understood it at that particular point. So lastly, I'll demonstrate for the sake of just understanding this last bit of resonance stabilized form that I talked about. And this is going to show that the more resonance stabilized compound is, the more stable it is. So in this case, I just going to do a quick demonstration for this. I'll have those 3 species. Maybe my drawings are not that well, but I hope that they'll be able to assist us. So I have that double bond at that particular point, and then lastly I have that one. So in this case, these 3 species are having hydrogen and an electrophile at that particular point. Hydrogen electrophile, hydrogen electrophile. Now that we have talked about how that one comes about. So in that case, if we have that kind of structure, resonance means these kinds of structure can be able to interchange to form each of the respective ones that we have just written. And in that case, when we are using the concept of this, we said that at this particular point there's a deficit of electrons, so we shall have this double bond moving at this double bond, that bond breakage moving at that point, and then we shall have this one moving at that point, whereby we have this one as the point that is having the charge. The last one that is we are having there, the charge is at that point. So in this case, the concept of this charge trying to move to different positions is what we call resonance. And the more structure or a compound which has resonance stabilized forms, the more stable it is. So this concept of electrophilic substitution is part of the reactions that we're going to learn, among others, in organic or aromatic chemistry, and it's going to assist us, of course, to know different reactions that we're going to encounter later, maybe in the topic of organic synthesis and others, which are going to assume the similar format. So in this case, apart from this, of course, I've talked about the substitution reactions. Other organic reactions that we're going to cover, which are going to precede this, of course, is addition reactions, elimination, and of course oxidation or rearrangement reactions that pertains to aromatic compounds. So in that case, I hope that this concept has been understood well. So in any case, we have not still, we shall have some of the supplementary discussions that we're going to do on this concept of aromatic chemistry, so that we can be able to get the concept and be able to apply it accordingly. So for that case today, that is it. So thank you guys. Bye. God bless you.